Okay, so we're diving into the world of mathematics today. But not to worry, we're ditching the dry textbook approach for something much more engaging.
Definitely more fun.
We're going on a journey through history with Le Grand Roland des Maths. It's by Mickaël Launay,
Great book, by the way.
and our mission is to uncover the unexpected beauty. And yes, even the delight hidden within a subject so many find, well, intimidating.
What I find fascinating is how Launay reminds us that we're actually engaging with math constantly in our daily lives, even when we don't realize it.
It's so true. When you're figuring out the best deal at the grocery store, or even just catching a ball.
There's math happening in the background all the time.
Exactly. Launay actually observed this disconnect at a public event himself. He found that people were way more drawn to geometric patterns and puzzles than when he presented the same concepts as mathematics.
It's amazing how much our perception can shape our interest in something.
It's like this mental block so many of us have. It's like, I'm not a math person. But what if we shifted that perspective? What if instead of rigid rules, math was this incredible tool humans have been shaping for millennia?
It's about changing the narrative.
Launay takes us all the way back to prehistory to make this point. Can you imagine our ancestors crafting perfectly symmetrical hand axes without any formal system of geometry or measurement?
Those hand axes are a powerful testament to early spatial reasoning. The symmetry wasn't accidental, it served a purpose. They understood balance and form.
And then there are those incredible patterns on Mesopotamian pottery.
Don't even get me started on those.
They're so intricate, and to think they predate the invention of writing.
It's mind-blowing, really. They discovered all 7 possible frieze patterns, long before anyone had put names to them.
It's like they were tapping into this hidden language of geometry without even realizing it.
Exactly. They had an intuitive understanding of order and structure, a way of making sense of the world around them.
It makes you wonder what else they were capable of understanding.
And then we get this pivotal moment. The Sumerians invent writing.
And for what may seem like a very basic need now, keeping track of livestock.
It seems simple, but that shift marked the birth of abstract mathematical thought.
Because they needed a way to represent those numbers.
Exactly. By creating symbols for numbers, they separated the concept of 5 from 5 sheep or 5 sacks of grain.
So it became more than just counting, it became about the quantities themselves.
Precisely. Suddenly, numbers could exist on their own, representing any quantity, allowing for more complex calculations and problem solving.
So it's not just about sheep anymore. It's about the power of abstraction, the ability to think about quantities and relationships without being tied to specific objects.
That's a huge leap forward. And as we move through history, we'll see how this ability to think abstractly allowed humans to solve increasingly complex problems, leading to some truly groundbreaking discoveries.
Like trying to figure out the problem of the Nile River flooding every year.
And the ancient Egyptians had to figure out how to reestablish property boundaries after the water receded.
Talk about a practical use for geometry.
Exactly. They developed these really sophisticated surveying techniques that relied on geometric principles to calculate areas and volumes with remarkable accuracy.
So they needed a way to be accurate and fair.
And then there were the Greeks. Now, they were also interested in the how, but they were obsessed with the why behind mathematical principles.
They weren't just satisfied with knowing something worked, they had to know why.
Exactly. Like Thales, he's considered the father of Greek mathematics. He demonstrated basic geometric theorems, things we might take for granted now, like a circle being divided into 2 equal halves by its diameter.
And they had to prove it.
That emphasis on proof became a hallmark of Greek mathematics. They weren't content with simply observing patterns. They wanted to understand the underlying logic, the universal truths behind those patterns.
Which led them to tackle some big questions about the world around them.
Like the size of our planet, for example.
Okay, but how do you even begin to calculate the Earth's circumference, centuries before satellites and modern technology?
That's the incredible part. It's mind-boggling.
Eratosthenes used simple observations and a bit of geometry to get its surprisingly accurate measurement.
It just goes to show the power of deductive reasoning. These ancient mathematicians were true pioneers, pushing the boundaries of human knowledge and laying the foundation for centuries of future discoveries.
It's amazing when you think about it, those same geometric principles that Eratosthenes used are also found in everyday objects all around us.
Wait, really? Like what? Don't tell me my coffee mug is secretly a mathematical marvel.
Maybe not your coffee mug, but remember those soccer balls we were talking about? They're not made of perfectly round pieces of leather, are they?
Now that you mention it, they're kind of hexagonal, right?
Exactly. A soccer ball is a truncated icosahedron.
Say that 5 times fast?
It's basically a shape with 20 hexagons and 12 pentagons all fitted together.
So that's what gives it that almost perfect spherical shape.
Precisely. And it's still possible to make it from those flat pieces.
Wow, I had no idea. So geometry really is the unsung hero of the beautiful game. And it goes way beyond sports, too. Think about architecture. The Géode in Paris, that giant mirrored sphere, it's based on an icosahedron.
One of the 5 regular polyhedron. Can Plato have some theories about those?
He did. Plato was obsessed with those 5 shapes. The tetrahedron, cube, octahedron, dodecahedron, and of course the icosahedron.
I'm trying to picture all of those at once.
He even associated them with the elements of the cosmos: fire, earth, air, water, and the universe itself.
Right. I remember learning about that. It's fascinating, even if it didn't quite hold up scientifically. I love that he saw that connection between these perfect shapes and the universe.
It speaks to our desire to find those patterns and that underlying order in the world. And speaking of patterns, there's perhaps no number more captivating in its seeming randomness than pi.
Pi. Oh boy. The one that just goes on and on forever.
Exactly. An irrational number, meaning its decimal representation goes on infinitely without repeating.
I remember trying to memorize all those digits in school.
It can feel impossible.
It felt like this big mystery. How can a number just never end?
That's what makes it so fascinating. This abstract concept tied to something very real. The ratio of a circle's circumference to its diameter.
So every circle, no matter how big or small, holds that same infinite ratio.
Precisely.
It's kind of beautiful when you think about it that way.
Launay describes a celebration for Pi Day at the Palais de la Découverte in Paris, where they have hundreds of pi's digits spiraling around a room.
It's like trying to capture infinity in a physical space. How do they even calculate something like that with so many digits?
Well, centuries ago, Archimedes dedicated himself to calculating pi with more and more precision.
Must have taken him forever.
He used a method of inscribing and circumscribing polygons around a circle.
So he was getting closer and closer to the true value with each calculation.
Exactly. Even back then, they understood the importance of accuracy. It makes you appreciate the dedication of those early mathematicians.
It really does. But it wasn't just about numbers like pi, right? They were also coming up with whole new ways of thinking about and organizing mathematical ideas.
Absolutely. And we'd be remiss not to mention the contributions of Arabic mathematicians.
Often recognized for their advancements in trigonometry.
Right. But their work in algebra was truly revolutionary.
Because when most people hear algebra, they think, oh no, not X and Y again.
It's so much more than that. Think about Al-Khwarizmi. His name actually gives us the word algorithm.
No way. I never knew that.
He developed a system for solving equations that moved away from concrete situations.
Instead of just trying to divide up land or inheritances.
He focused on the pure mathematical relationships.
So it's like he created a new language for those ideas.
Precisely. A more concise, powerful, and ultimately universal language. And with it, mathematicians could explore even more complex patterns and relationships.
Like the Fibonacci sequence.
You got it.
That's the one where each number is the sum of the two before it, right? 1, 1, 2, 3, 5, 8, and so on.
You've got a good memory. And here's the fascinating part. The Fibonacci sequence pops up in the most unexpected places.
Like where?
The arrangement of seeds in a sunflower, the branching patterns of trees, even the proportions of the human body.
Like this secret code running through nature.
And it's closely related to the golden ratio. This special number found in art, architecture, and nature as well.
So we've gone from recognizing those simple patterns and hand axes to these complex systems of thought. It's amazing how far our understanding of math has come.
And we're still discovering more. This journey is far from over.
You said this journey isn't over, and honestly, my mind is already pretty blown. Where do we even go from here? What other mathematical mountains are left to climb?
Well, we've covered patterns, numbers, shapes. But there's one concept that's both fundamental to math and completely mind-boggling. Infinity.
Infinity.
Yeah.
That's always a bit of a head-scratcher back in my school days. It just goes on forever, right? How can you even wrap your head around something like that?
It's puzzled mathematicians for centuries. Launay takes us back to ancient Greece to illustrate this with Zeno's paradoxes.
Zeno's paradoxes. Okay, those ring a bell. What were they again?
Thought experiments designed to show just how counterintuitive infinity can be.
Counterintuitive, how so?
Think about the paradox of Achilles and the tortoise Achilles. A swift hero is challenged to a race by a tortoise. To make it fair, the tortoise gets a head start. Zeno argues Achilles can never actually overtake the tortoise.
I mean, that doesn't sound right. Achilles is supposed to be super fast.
That's the point. Zeno says to overtake the tortoise, Achilles first has to cover half the distance between them, then half the remaining distance, and so on. An infinite series of ever smaller distances.
So even though we know Achilles should win the paradox, highlights how strange it is to think about infinity practically.
Exactly. It's like trying to reach the end of a rainbow. And this is where calculus comes in.
Calculus. Ah, yes, derivatives and integrals. How does that help with infinity?
Calculus gives us the tools to deal with infinity. Not just as a concept, but practically. It lets us analyze continuous change in motion.
By working with those infinitely small quantities.
Precisely. Think of a perfectly smooth curve. It's made up of individual points, but those points have no dimension. So how can they form a continuous line?
It's like those points are there and not there at the same time.
That's the beauty of it. Calculus bridges that gap between the infinitely small and the finitely measurable. It's how we can understand things like instantaneous velocity or the area under a curve.
Things that traditional geometry and algebra couldn't quite grasp.
Exactly. Calculus gave us a new way to describe and understand the world, one that could handle both the continuous and the discrete.
And it's used everywhere, isn't it?
Everywhere, from physics and engineering to economics and biology.
It really makes you wonder, is math something we invent or something we discover? It feels almost like it's already embedded in the fabric of the universe.
That's a question that's been debated for ages. Launay talks about the unreasonable effectiveness of mathematics.
Unreasonable how so?
The way these equations can express such profound truths about reality, like Newton's law of universal gravitation or Einstein's EMCs.
Those are some heavy hitters.
Exactly. They're not just tools for calculation. They're like glimpses into the fundamental workings of the universe.
It's almost as if math is the language of the universe. And we're just starting to learn the vocabulary.
And that's where Launay leaves us. To ponder the question, is math invented or discovered? It's a question without an easy answer.
But one worth exploring.
Absolutely. It's a question that can lead to a lifetime of curiosity and wonder.
This whole deep dive has been eye-opening. It's not just about formulas and equations. It's about human curiosity, the evolution of thought, and this incredible language we use to understand our place in the universe.
And it reminds us that anyone can appreciate the beauty and wonder of math. You don't have to be a mathematician to appreciate its elegance and its power.
It's a journey we can all take. So to our listeners out there, keep exploring, keep questioning, and keep marveling at the unexpected beauty of math.